Hello everyone, welcome to the Material Science class MIG 300. This is part 2 of chapter 3. This chapter we are discussing the structure of crystalline solids. Over part 1 we explained what does it mean a crystalline solid or a crystalline material, the difference between a crystalline material and an amorphous material. Also we discussed the unit cell, the crystal structure. In the meanwhile, we discussed three commonly crystal structures that commonly found in metals, which are the FCC, BCC, and HCB crystal structure. And we compared between them in terms of the geometry, in terms of the coordination number, and the atomic backing factors. In the meanwhile, I showed you how we can do the calculation for the coordination number and the atomic backing factor for these three crystals. In this part 2, we're going to learn some new skills, some other things to calculate for crystal structures in general, especially the HCB, BCC, and the FCC crystal structures. We're going to know how we can allocate the point or the location of a point within a unit cell of this crystal, which is known as the crystallographic point. Also, I'm gonna show you how we can do the calculations or define a direction within the unit cell known as the crystallographic direction. Also, how we can define a plane within a unit cell known as the crystallographic plane. So we're gonna focus over this part 2 over three things. We're gonna know how we can define point, direction, and plane within a unit cell. This part 2 will be covered over two videos. This is the first video of the part 2. Alright, so let us start with the crystal system. What is a crystal system? Crystal system, this is like a group or a system that describe a group of different crystal structures. Over the last video, we discussed three crystal structures: FCC, BCC, and HCB. And I mentioned that these are not the only crystal structure that we have. We do have so many types of crystal structures, but these are the commonly used one or found in metal, so that's why we explain them in detail. But the same thing that we already discussed over these three crystal structure, it can be applied to any other crystal structure. But the question is, how many crystal structures do we have in general? So actually we do have in general 7 crystal systems. We do have in general 7 crystal systems. Every one of these systems contain a set of different crystal structures. So generally, the crystal system can be defined as depending on the geometry of the crystal or the unit cell of the crystal. For example, a unit cell can be generally represented as 3D parallel piped with 3 edge lengths A, B, and C, as shown here in this figure. This edge length, it is A, which is parallel to X, and the edge that is parallel to Y, it is B, and the edge that is parallel to Z, it is C. So we're gonna fix these A, B, C in this order, in this way, like all the time. We're gonna fix this because this is what is commonly known by the material science field, that A indicates the length of the edge of the unit cell that is parallel to X. B indicates the length of the edge that is parallel to Y in the unit cell. C indicates the length of the edge that is parallel to Z in the unit cell. Also, as you can see, for this unit cell, as long as it is represented as parallel piped, it means that this X, Y, and Z, it is not necessary that the angles between them, it should be 90 degrees. They are representing a coordinate system, but a special coordinate system for this unit cell. It means that the angle between X and Y is gamma, the angle between Y and Z axes is alpha, and the angle between X and Z is beta. So that's why this geometry, this cuboid, it is represented by 3 edge lengths A, B, and C, and in the meanwhile by 3 angles, alpha, beta, and gamma. So we do have, let's say, we do have 7 arrangements of these 6 parameters that describe the geometry of this unit cell. The geometry of this unit cell is described by 6 parameters, 3 lengths and 3 angles. So they have 7 arrangements of these A, B, and C's, and the alpha, beta, and gamma. So what are the difference here? We do have the option that alpha could be 90 degree or it is not 90 degree. So it could be 90 or equal to 90 or it is not equal to 90. The same thing for beta and gamma. So this like 2 scenarios, 2 options. Either to have alpha 90 degrees or it is not 90 degree, any other value. The same thing for A, B, and C. For A, B, and C, it could like A could be equal to B or they are not equal. A could equal to B or they are not equal. Like for the case of cubic crystal. Cubic crystal, you should have A and B and C are equal lengths. A equals to B equal to C. And alpha, beta, and gamma are all equal to 90 degrees. So we have different arrangement. For example, these arrangements will be different for the hexagonal HCB crystal structure that we discussed last video. Like in HCB, we do have the A and B, they should be equal, but C is not equal to A or B. There is a difference between them. There is a relation between C and A and B. But A and B are equal for a hexagonal crystal structure, and alpha and beta, they are 90 degrees, but gamma, it is a different degree. It is 120 degrees, as I'm going to show you. So this means that depending on the arrangement or the relations between A, B, and C, alpha, beta, and gamma, whatever alpha, beta, and gamma equals to 90 degrees or not, their relation, this is going to define a crystal system. So the crystal system, it is defined, it is a representation, it is a way of representing a 3D parallelepiped of a unit cell of a certain crystal that depend on 3 edge lengths, A, B, and C, and 3 angles, alpha, beta, and gamma. Make sense? Some of the properties of crystalline solids, and this is what we have been discussing once we started chapter 3, depend on their crystal structure. As we mentioned, the density over the last video, it do depend on the crystal structure. So, and this is the objective of this chapter 3, just to understand how these arrangement of atoms, how these different crystal structure would influence the properties of the material, and this is what will be demonstrated further over the next chapters. There are 7 different possibilities or ways of combining the unit cell parameter A, B, and C, alpha, beta, and gamma, as I mentioned, each of which represent a distinct crystal system. So in total, we do have 7 crystal systems that depend on the combination and the arrangement of these and the relation between A, B, and C, alpha, beta, and gamma. For example, the simplest one of them is the cubic crystal structure that we discussed, and the example of these ones were the FCC crystal structure and the BCC crystal structure. So remember that the cubic system, here we are discussing the crystal system, is different than the crystal structure. The crystal system, it is like a family. It is like a group of different multiple crystal structures. So the one crystal system may contain many and different crystal structures. Make sense? So this is a group. So the cubic crystals, we discussed 2 types of them over the last video. We discussed 2 cubic crystal systems, or 2 cubic crystal structures that belong to one crystal system, which is the cubic crystal system. These were the FCC and BCC, but there are more than just these 2. So in the cubic, the A, since it means that the unit cell, the geometry of the unit cell should be cubic. It means that A, B, and C, the edge that is parallel to X, the edge that is parallel to Y, and Z, all they should be equal. They should be equal to A or B or C. You can give this letter A or B or C, it's up to you. Anyway, they all are equal. And the angles between X and Y, which is gamma, Y and Z, which is beta, and X and Z, which is alpha, all are equal to 90 degrees. This is for the cubic crystal system. For example, in the cubic crystal system, we do have, these are the common 3 types of crystal structure that located or defined as cubic crystal system. So this is the cubic crystal system. In the cubic crystal system, we do have 3 different crystal structures. We do have the FCC crystal structure that we discussed in the last video. Also, we do have the BCC crystal structure that also has been discussed over the last video. And we do have the simple cubic crystal structure. What is the simple cubic crystal structure? There are some metals, there are some ceramic material that their crystal structure, it is a simple cubic crystal structure, not BCC or FCC. So what is the difference? The difference between FCC and BCC, as we discussed the last video, is that there is an atom that is located at the center of every face in the FCC, but in the BCC crystal structure, we have one atom that is located in the core, and other atoms are located at the corner. In the simple cubic crystal, we do have atoms who are located at the corners of the unit cell, and that's it. There is no atoms at the centers of the faces like the case of FCC. There is no atom that is located in the core like the case of the body center cubic crystal. Make sense? So these are three different crystal structure. We do have some metal that they do have simple cubic crystal structure. We do have some other metal that they do have BCC. There are some other metal that they do have FCC. These three crystal structures located in one group, in one crystal system known as the cubic crystal system. Make sense? The second crystal system here, it is hexagonal. We discussed one of them, these hexagonal things, is the HCP. So this HCP, it was hexagonal close-packed crystal structure that was composed of three layers of different atoms, three layers of atom. There was a layer of atom that located or distributed over the top surface, and there was another layer of atom that is located or distributed over the bottom surface, and there was like three atoms distributed or arranged, forming a triangle inside in the middle layer, right? We probably do have another hexagonal crystal structure without the three atoms in the middle. Like there is a hexagonal crystal structure without the middle layer, only the top layer and the bottom layer, and that's it. So this is another crystal structure, hexagonal crystal structure. All of these different hexagonal crystal structures, they are located in one crystal system known as hexagonal crystal system. In the hexagonal crystal system, what is the common between all of them? The common between these different hexagonal crystal structure is that the A and B, which are the side edge that is parallel to x-axis, and the one that is parallel to y-axis, both are equal, but the one that is parallel to Z is likely to be unequal to this A or B. So A and B are equal sides, but C, it is a different side. For alpha and beta, the angle they are equal to 90 degrees, but the gamma angle, it is 120 degrees. What is the gamma? This is the angle between the X and Y in the base, referring to this reference. This is the standard. So the gamma is the angle between X-axis and Y-axis in this hexagonal crystal structure. Like for example, you're gonna find that this is Y-axis, and this is X-axis, and this is gonna be the vertical, it's gonna be the Z-axis. So the angle between X and Y, it is not 90 degrees. In the hexagonal crystal structure, it is 120 degrees. But the angle between X and Z, or Y and Z, it is 90 degrees. So that's why alpha and beta, they are 90s, but also A and B are equal, but the height C, it is different. So this is the HCB. For the HCB, for example, we do have the commonly shown thing, which is hexagonal, close back. Close back, it means that we're gonna add three other atoms. But the hexagonal crystal structure is the one without the middle layer, without the three atoms that located in the middle. If we remove them, we do have another crystal structure. This is gonna be known as hexagonal crystal structure. So we do have hexagonal crystal structure, and we do have hexagonal closed back crystal structure. The hexagonal closed back, it will contain three layers, but the hexagonal crystal structure contain only two layers of atoms. The one on the top, the one on the bottom, and that's it. There is no the middle layer. Make sense? So both are located in one system known as the hexagonal crystal system. In addition to these systems, also we do have the tetragonal crystal system that has A and B are equal, but C is different, but alpha, beta, and gamma all are equal to 90 degrees. So it is very similar to the hexagonal, but the difference is this angle, it is 120, here it is 90 degrees. And we do have another type which is known as trigonal or the rhombohedral crystal system, which has A, B, and C are equal, like the cubic crystal structure, but alpha, beta, and gamma, they are not 90 degrees. They are any other angle that is different than 90. If this is 90, this becomes the cubic crystal structure. We have also the orthorhombic crystal structure that has A, B, and C are not equal, and alpha, beta, and gamma, they are 90 degrees. So all the edges are not equal, very similar to the cubic, but in terms of the angle, but in terms of the side edges, they are not equal. This is gonna give us the orthorhombic crystal system. And monoclinic, we do have the A, B, and C, they are not equal. Alpha and gamma, they are 90 degrees, but beta, it will be any other angle that is not 90 degree. The triclinic, it is A, B, and C are not equal. Alpha, beta, and gamma, none of them is equal to 90 degree. This gives the 7 crystal structures. These are the 7 possibilities of arranging these 6 parameters, the side edges, which A, B, and C, and the angles alpha, beta, and gamma to form this crystal system. So as we mentioned, every one of these crystal systems contain a set of different crystal structure. Like the cubic crystal system has 3. Like for example, this is the tetragonal crystal structure, has simple tetragonal, and it has body center tetragonal crystal structure. It means that there should be an atom that located at the corner of this, at every corner, and there is one atom that is located in the core. So there is body center tetragonal crystal structure. Some of the metals or crystalline or ceramic material, they may have this unit cell of the crystal structure, or they could be simple tetragonal crystal structure. Also the orthorhombic, we do have the simple body center, base centered, face center. Base center, for example, that there should be an atom that is located at every corner, and there should be one atom here, and there is an atom that is located at the center of the top face and the bottom face only. So that's why it is base centered crystal structure. But this one is face centered orthorhombic crystal structure that has at every corner there is an atom, at the center of every face there is an atom. But also we do have the symbol and the body center, and so on. So it means that, as I mentioned, for every one of these crystal systems, there are a group of different crystal structures. So this indicates that we don't have only 3 crystal structures. No, we have a bunch of them, many of them, but the most common ones that found in many of metallic material are the 3 that we already covered over the part 1, which are the FCC, BCC, and the HCB crystal structures. Make sense? Now let us move to another point here, which is how we can define a point within a specific unit system, whatever it is, cubic, tetragonal, or rhombic, belong to any one of these systems, we don't care. But anyway, you do have a certain unit cell, and you are required to locate or define the location of a certain point within this crystal unit cell. This is known as crystallographic point. Crystallographic point, or point that define the location of an atom or anything inside this unit cell. Anything definitely is going to be an atom. Like we are likely define the locations of atoms inside the unit cell itself. So how we can define this? Your objective is just to set up the X, Y, Z, which are the coordinate system for this unit cell. But remember, this is a special coordinate system. The coordinate system that we knew from engineering, that it should be the X, Y, and Z, the angles between them should be 90 degrees. Like alpha, beta, and gamma, they should be 90s. But this is not necessary here. This depends on which crystal system that you are dealing with. We may have alpha, gamma, or beta. None of them is 90 degrees. It means that you're going to set up the X, Y, and Z in general, and it is not necessary that the angle between them are 90 degrees. You're going to still deal with it like this X, Y, and Z, like they are the coordinate system as we used to do for the engineering application in previous courses. But remember that this should be like a special coordinate system for this unit cell, that it would be inclined, or the angle between these axes, it is not necessary to be 90 degrees. So in general, we do have X, Y, and Z, and there should be one point like point P, and we would like to define the location of this point. So we're going to do the same thing that we used to do for engineering application in previous courses. If I ask you to define the point or the coordinate of this point, what you're going to do, you're just going to imagine that you start from the 0 point, then you're going to move parallel to X a certain distance, then you're going to move parallel to Y a certain distance, and then you're going to jump parallel to Z a certain distance till you reach to that point. But moving along X, Y, and Z, it is not necessary to be like in a straight line. You know, you could, for example, move inclined, but the key condition that you have to move parallel to the Z axis, parallel to the Y axis, parallel to the X axis, as already shown here. So for example, if you're standing here and you're going to move parallel to X, a distance as QA. So the Q, this is the distance. What is A? This is the side edge of the edge of the unit cell that is parallel to X. We agreed before that A, B, and C, these are define the lengths of the edges who are parallel to X, Y, and Z respectively. What does it mean? It means that A belongs to the edge that is parallel to X, B is the edge that is parallel to Y, C is the edge that is parallel to Z for any one of these 7 crystal systems. So if you're standing here, how long you gonna move in terms of A? Half of it or the entire A? 3/4 of A, quarter of A, it depends. So I'm gonna move a Q distance of A, like a fraction of A, a percent of A. I won't gonna move 100% of that A. I move, for example, 60%. So this Q represents the fraction, the percent of the distance that you're gonna move parallel to X in terms of the edge side of the length of the length A. The same thing for Y. RB, I'm gonna move parallel to Y, RB distance, where R stands as a fraction, a percent of this B. What is B? This is the side edge that is parallel to Y. This is the length of this side edge that is parallel to Y. The same thing for C. I'm gonna jump parallel to Z with the distance as SC. So S stands for another fraction for the C. So how we can write the point, the crystallographic point for this unit cell? You're gonna say that point P equals, it means that you're gonna define the location of that point, Q, R, and S, that's it. You're gonna divide by A. You're gonna divide by B. You're gonna divide by C. It means that you're just gonna mention the fractions of these side edges. And you're gonna put them without any bracket, without any parentheses, without anything. Just you're gonna put 3 fractions next to each other, and that's it. There is no commas, there is nothing. This is how we are representing a point, a crystallographic point that defines the location of an atom, for example, inside a unit cell. It is highly important to represent them the same way, because this is a standard approach, this is a standard methods that all engineering scientists or materials engineers or all material scientists, they are dealing with these points with this way. Like we do have a fraction, another fraction that indicate that what is the percent of the travel along A edge, what is the percent of the travel parallel to the or along the B edge, what is the travel fraction, the percent of the travel along the C edge. These are the fractions. So for example, if you are required, or let us start with this one, let us specify the points, the point coordinates, the crystallographic points or the point coordinates of all atoms, of all atom positions of BCC crystal unit cell. We said that a BCC crystal structure or unit cell contains atoms at every corner, right? And there should be an atom that is located in the core. In the meanwhile, this is the atom 5, which is located in the core of this cube. So the FCC crystal structure, it is a cubic unit cell. So you're gonna draw a cubic unit cell. Then you're gonna distribute the atom. There should be an atom at every corner, as we discussed over the last video, and there should be one atom in the core, which is atom 5. Then you can give them names. Then we're gonna set up the X, Y, Z axes according to the, since it is cubic crystal, so it should belong to this crystal system, which is cubic. In the cubic, the all edges, they should be equal, A, B, C, and are equal, and the angle should be 90 degrees. Since it is cubic, very simple, right? So if I ask you to define the coordinates of this point 1, this atom 1, it is required to find the coordinates or the point coordinates of all atom positions of within the BCC crystal structure. So if I ask you what is the coordinate of this point 1, this should be the 0 point. So it's 0, 0, 0. You're gonna move nothing along X, Y, or Z. So it means that you're gonna move 0 of A and 0 of B and 0 of C. Then if you divide by A, by B, by C, you're gonna end up with 0, 0, 0, which gives the coordinate of the first atom. Very simple. There is no brackets, there is no commas, there is no square bracket, parentheses, there is nothing. Just put the numbers or the fractions next to each other, and that's it. And that is fine. Any one of these index, every one of this number is known as index for this crystallographic point. Every one of this index of this crystallographic point, it could be integer value, it could be fraction. It doesn't matter. Make sense? For example, let us choose point 3. If I ask you to locate the coordinates of point 3, or atom 3, what you're gonna do? You're gonna start from the 0. How long you're gonna move parallel to x? I'm gonna move the 100% of A. I'm gonna move the entire edge. I'm gonna move the entire A. So I do have here, for this case, for atom 3, So what I'm gonna do, I'm gonna move the entire A, like 100% or 1 of A. How long? So till you reach this point, how long you're gonna move parallel to Y? You're gonna move the entire edge B, which is 1B, which is also equal to A. Remember that in cubic crystal, A is equal to B. So you can even write A here, it doesn't matter. Then, do you move anything parallel to Z? No, so I'm gonna move 0% of C. Then you're gonna divide by A, by B, by C. This is gonna give us 1, 1, 0. So these are the point. There is no brackets, parentheses, there is no commas. So for point 3 or atom 3, the coordinate for this atom, it is 1, 1, 0. And that's it. Very simple, right? How about atom 5, which is located in the core? In the core, it means that if you start from the 0 point to reach to the core, like the middle, the core in your room, the cubic shape, you're gonna start from here, moving parallel to x half of the edge A, half of it. So for point 5, you're gonna move half of the A, right? Then you're gonna move half of the B, which is parallel to Y, so half of the B. And then you're gonna jump up parallel to Z, but you're gonna move half of the C, half of the height, till you reach to point 5, because point 5 or atom 5 is located in the middle, in the core of this cubic shape. So you're gonna move half along X, half along Y, half along the C. Then if you divide by A, by B, by C, this is gonna give us half, 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 half. So you're just gonna arrange these 3 indices, indicating that you're gonna move half of this edge, half of this edge, half of the height to reach to the point 5. And so on. You can repeat for the other point. You're gonna find that is very simple, very straightforward method to locate the point. The key condition is that there is no parentheses, there is no commas. This is not the conventional way of representing points. It is the same approach that we are using, for example, in the mathematics or linear algebra. If you are required to specify a point, you're just gonna move parallel to X, Y, and Z. Then you're gonna put the points as X, comma, Y, comma, Z, right, in 2 parentheses. But here we are not using parentheses, we are not using commas, but it's still the same approach. Make sense? For example, for this case, it is required to locate. It means that you're gonna draw the point having the coordinate within this crystal structure. This is a unit cell for a specific crystal structure. We don't know what is the type of this crystal structure exactly is, and we are not interested. Like this is X, Y, and Z already given to you, and you are required to locate this point, to draw this point over this graph. So according to the point specification, the indices of this point, we do have quarter of A and 1%, the entire B, and we do have half of C, right? This is according to the quarter 1.5 that we already given here. Make sense? It means that you should move parallel to X, because this is X, Y, and Z. You should move parallel to X, quarter of A edge. How long is the A edge? A edge, this is the edge that is parallel to X. So this 0.48 nanometer, this should equal to A. So A equals 0.48 nanometer, but B equals to 0.46 nanometer, but C equals 0.4 nanometer. This is how we specify all the time. A is conjugate to C, X axis, B conjugate to Y, C is conjugate to Z axis. Make sense? So you should move quarter of A, if you divide 0.48 over 4 or multiply times quarter, this is going to give us 0.12 nanometer. It means that you're going to move, starting from the 0, you should move parallel to x 0.12 nanometer along x. Then you're going to move parallel to y, so you're going to move a distance 0.12 nanometer. Then you're going to move parallel to y, the entire y, right? So you're going to move the entire distance because y is 100% or 1. Then you're going to move parallel to z. Remember that parallel to z should be inclined parallel to z. How long? Half of the c. The c is 0.4 nanometer. It means that you should jump up with 0.2 nanometer, half of it, half of this height, till you reach to this point. So this should be the point B with these coordinate or crystallographic coordinates. Make sense? So this is simply how we can define a point within a unit cell. It is a straightforward method, but remember, again, there is no comma, there is no parentheses. The same approach as we used to define points before, but the representation of these indices, it would be different. Make sense? Let us move to the crystallographic direction. So we discussed a point, how we can locate a point, how we can locate the location, define the coordinates or the equation of an atom. Now, how about the direction? Direction from mathematics, it is a vector. The direction, it should be a vector that is set up between 2 points or 3 points or whatever. Like in general, it should be like 2 points. Like you do have a start point and end point to indicate that this is the direction, right? So we're gonna do the same thing. Like it means that you should have one atom and another atom, and you would like to specify the direction that these two atoms represent. Why this crystallographic direction thing is important, it's going to be much more important when we discuss the crystallographic direction between the, and how we can distinguish between one grain and another grain. As I explained before once in the start of this course, we said that the grains, what distinguish one grain from the other one, that the atoms here, they are arranged and they do have a certain crystallographic direction, but the atoms in the other grain, they do have a different crystallographic direction. So what does it mean, crystallographic direction, and how we can define this thing? This is what we are going to explain here. So a crystallographic direction is defined by a line or a vector between any 2 points or any 2 atoms in a unit cell. Very simple. To draw a line between any two points, it is not necessary to be one of these points and the 0 point. No, any 2 points that belong to the unit cell, if you set up a vector between them, this is gonna define a crystallographic direction. How we can define this crystallographic direction? This is what we are going to say. The crystallographic direction is represented as a composition of 3 or 4 indices, depending on what? Depending on the crystal system. We have 7 crystal systems. Some of them are cubic, some of them are hexagonal, for example. For the cubic, 3 indices are enough. For the hexagonal, it is preferred to use 4 indices, as I'm going to show you. Okay? The 4 indices, it would be something weird. Because, for example, if I ask you to describe a vector from the mathematical point of view, any vector, it should have like I, J, and K, which X value, Y value, and Z value. So in general, from mathematics, any vector, it has 3 indices. It has 3 values, X, Y, and Z. How about the 4th one? This is a special case for the hexagonal crystal structure, as it will be explained. But in general, the crystallographic direction, it is a vector, like the conventional vector that we are dealing with in mathematics, that is set up between any 2 points. This crystallographic direction, it could be represented by 3 indices or 4. And they should be confined or collected in a square bracket with no commas. The representation of the vector is a big deal. You're just gonna put 3 indices or 4 indices, depending on the crystal system. Then you're gonna confine them in a square bracket with no commas. But if we remove the square bracket, this indicates a point. So the representation, it is a big deal. So how we can define, this is the procedure, these are the steps to define the crystallographic direction between any 2 points that belong to any unit cell. How we can do it? We basically start from the start point. You're going to consider, as I mentioned, there should be a vector set up between 2 points. you're gonna pick any one of these 2 points because the vector will be represented in this way. Like we have the 0, this is the start, and it's gonna be directed. So this is gonna be the start point, and definitely this is gonna be the end point. So from the start point, which would be the origin of the coordinate system, you can assume that this is like the 0. So you're gonna deal with this start, like this is the coordinate. This is the origin of the coordinate system. This is the 0 point. Then you're gonna measure. Draw the vector from the origin point, which this start point, to the other point along this unit cell. Find the projections. This is the approach. One of the approaches, as explained in the textbook, is just to find the projections of the vector along all sides of the unit cell. We have 3 sides of the unit cell, parallel to X, Y, or Z. So your objective is just to find the projections of this vector along X, along Y, along Z. These projections are determined in terms of the lengths of these sides of the unit cell. The determined projections are then multiplied, and this is a very important step. That the condition is that all of these indices, all of them should be integers. But the indices in the points, that is fine, you may have an index that is a fraction. This is for the points. As we discussed for the points, we said that we may use fraction. So these indices in the point crystallographic would be fractions or integers. But for the crystallographic directions, all indices should be integer values. This is the condition. There is no crystallographic direction that can be defined by a fraction. The indices, all of them should be integers. So that's why in case that you don't have fractions within the calculation, when you calculate the projections, definitely you would end up with some fractions. Your objective is just to multiply all of these indices, all of them, by the same value, by the same integer number, to reduce them to the smallest integer value. The smallest, this is the condition. You have to seek the smallest integer value. You're just gonna choose a number, any integer number, and you're gonna multiply all the indices together by the same number to end up that all of them are integers, the smallest integer set. This is gonna define the crystallographic direction, and I'm gonna show you how we can do it with more detail. This gives the indices of the crystallographic direction. Then we are enclosing them in a square bracket without any commas. So this is the procedure. So to understand it more, let us start here with this thing, with this example. Assume that you already given this unit cell, and you are required to determine the indices for the direction shown in this figure. So what is the direction? The direction starts from here. This is the start point, and this is the end point. So according to this procedure as explained in the textbook, your objective is just to find the projections of this vector along X, Y, and Z. So what is the projection of this edge or this vector along the X direction? It is half of A. Assume that as already represented here, this is what is given. So it is half of A. So along the X-axis, we do have half of A. Along Y-axis, we do have the entire B, right? The projection of this vector along Y-axis, it is the entire B, so it is 1B. Along Z-axis, we do have nothing. We're not gonna move anything. There is no projection along Z-axis, so it is 0C. This is if you decided to work with the projections, but it would be a little bit complicated. But the easiest approach is that you choose where is the start point. The start point all the time, it should be the base of this vector. So this definitely is going to be the start point, and define where is the end point. Then your objective is just to stop at the start, or start from the start point and move. Like you locate a point as we explained before for the point. This is the, forget about the projections, it would be complicated for some of you. The easiest way, choose the start point, locate the start point, then move from the start point to the end point, parallel to X, Y, and Z, and find the distances. How long you should move parallel to X? You should move half of A. How long you should move parallel to Y? You should move the entire B, which is 1B. How long you should move parallel to Z? I won't gonna move nothing because I already reached to the point. There is no movement in the Z direction. It means that you'd have 0C. Make sense? So what are the indices now? The indices should be half and 1 and 0. Like you're already locating points, locating the other endpoint from the start point. But if you confine these three indices in a square bracket, this gives the crystallographic direction. Without the square brackets, you are defining the endpoint. You are defining the crystallographic point of this endpoint. But we need to define the direction. You should use a square bracket. But before using the square bracket, you have another condition is that all of these indices should be integers. I do have this 0, it is integer 0. The multiplication 0 multiplied by any number is just 0. 1 is already integer, but I do have a fraction here. I have to get rid of this half. How? You should multiply all of these three indices by a number that is common. One single number multiplied by all of them. This number, it should provide this all of them integer, but the smallest integer. So how we can define it? Your objective is just to look to the denominator of the fraction, because you probably may have more than one fraction. Here I do have only one fraction, so you're gonna multiply all the indices by the value of this denominator of this fraction. So the denominator here is 2. So what you're gonna do, you're just gonna multiply times 2, times 2, times 2. Why 2? You're just gonna choose the largest denominator and multiply by this value. So this is gonna give us here 1 and 2 and 0. Then you're gonna confine them in a square bracket. This is gonna give you the crystallographic direction that is given here, which is 1, 2, 0. You could add space here or without a space, it doesn't matter. Like in many of the cases, we don't use spaces. It means that when we read this thing, it is not 120. It is 1, 2, 0 crystallographic direction. Make sense? So this is the crystallographic direction for this vector, how we can deal with it for this crystal structure. All right, so for this example, it is required to draw. So the previous example, the vector was already given, and you were required to find the indices of this vector. Now, how about if the indices are given and you are required to draw the vector? So you should know the two skills. For a given vector, what should be the indices? For a given indices, what should be the vector? Draw the vector. So it is required to draw this vector direction, within a cubic unit cell. So the cubic unit cell, you're gonna draw the cubic unit cell, which is commonly known. It is well known that it has all the side edges are are equal, and the angles are 90 degrees. It is cubic crystal system. So we do have A, and X, Y, and Z as already shown here. And this is gonna be the 0 point. It is required to draw this crystallographic direction. So I have to do some things about this crystallographic direction. We do have something new here, which is this bar on the top of this one. This bar indicates that this index, it is a -1. So for example, I can write this one as 1, -1, 0. You got my point? But in terms of the representation of the crystallographic direction, this is not preferred, because I could deal with this like a dash, not a negative. As long as I mentioned, we basically don't add spaces here. Normally or commonly, we are not add spacing. We remove the space between these indices. We just put 1, 2, 0 next to each other. So if we remove the space, so is it dash or is it negative? So we agreed to represent this one in this way, like to be 1, -1. So the dash for the negative sign, it will be on the top of the index, the top of the number, 0. So this crystallographic direction indicator is 1, -1, 0. You got it? So if this is the crystallographic direction, it means that you should move the entire A along x-axis, and the -1 of B. -1 of B, it means that instead of moving parallel to in the positive y direction, you're gonna move in the negative y direction. So the -1 here indicates that you're gonna move in the negative direction of this vector, or this direction. or this axis. This axis here, it is y-axis. So you're gonna move in the negative y the entire, how long? What is the distance? The entire B edge. And you're gonna move 0C. It means that it should be located over the XY plane. So, and this is what you're gonna do. So you're gonna start from the 0 point, move the entire A, move the entire X, move the entire edge that is parallel to X. So I'm gonna move the entire edge that is parallel to X till I reach to this point. So now I'm here. Then you're gonna move to the negative Y with the entire distance of B. So B, which is this edge, and instead of moving this direction, you're gonna move the other direction with a negative A, with the negative entire A or B distance, which is A since this is cubic. Then you aren't gonna move nothing. You will not move anything along the Z direction. It means that this should be the B point. So this is the start point. You started from here and you end up here. Then your objective is just to connect these 2 points with a vector. This is gonna define the crystallographic direction 1, negative 1, 0. We read it this way, 1, negative 1, 0. Make sense? So these are also in cubic crystals. So far we're just discussing how we can define these crystallographic directions in general, and especially for the cubic crystals. For cubic crystal, these are some of the common directions that we could find in any cubic crystal. Like for example, this direction, it is like, let us start with this one. This direction here, it is 1, 0, 0. Why? Because 1, 0, 0, it means that you will start from the 0 point, moving 1 along X. 1 along X, it means that you're gonna move the entire edge, and you are gonna move nothing parallel to Y or Z. It means that this is gonna be the end point. So this is gonna give us the 1, 0, 0 direction. This blue direction, it is 1, 1, 0. Why 1, 1, 0? Because you start from here, you're gonna move 1A, 1B, and 0C. So this is gonna be the end point. This direction, it is 1, 1, 1 direction. So what does it mean? It means that you're gonna move parallel to X, 1A, 1B, 1C, till you reach to the end point. Very simple, right? How about this direction? The other directions are the same. This is still 1, 1, 0. This is still 1, 0, 0. This is 1, 0, 1. So you're gonna move this vector, for example, this vector, you're gonna move parallel to X, 1, 0, Y, then you're gonna move parallel to Z, 1C. So this is gonna give us 1, 0, 1. How about this vector? What are the indices of this vector? This vector connects the 0 point to the center of the top face, like the FCC crystal structure. Assume that there is an atom here that is located at the center of this top surface or face. So what should be this vector? If I ask you to start from here, move till this end point, how long you're gonna move parallel to X, parallel to Y, parallel to Z? You can, to make it easy, it is not necessary to start all the time moving parallel to X, then Y or Z. No, you can do any arrangement. You can start moving parallel to Z, then Y, then X. Or parallel to Z, then X, then Y. It doesn't matter. Anyway, you should have 3 indices. One index along the X direction, one index along the Z direction, Y direction, and Z direction. So for example, for this index here, for this vector, I'm gonna start moving parallel to Z first. This is gonna be much more easy, right? So how can you jump? Because this point is located in the center of the top surface. So I need to reach to that top surface first, right? So how can I move? What should I move? Parallel to Z to reach to the top surface, you have to move the entire C distance. The whole C distance over this edge. So I'm gonna move over this edge up till this point, right? This total height, it is 1C. So I moved parallel to Z, 1C. Then what? I reach up to this point. Then you should move parallel to X, half, because this is located in the center of this top surface, right? So you're gonna move half of the X, half of A, till you reach to this point. So I'm gonna move half of A till this point. Then you're gonna move half of Y, which is half of B, till you reach to the end point. So I'm gonna move half of B till I reach to the end point. Make sense? Very simple. So I started with Z, then X, then Y. If you are interested to start with X, then Y, then Z, it's up to you. Anyway, you're gonna reach to the same point. It doesn't matter which index you start with first. Then your objective is just to divide. Get rid of A, B, and C, like you're already dividing by these edges. So you're gonna end up with half, half, and 1. Remember that since we are dealing with crystallographic directions, these halves, we should get rid of them. We should use integer indices. So it means that you're gonna multiply all the indices by the largest denominator. The largest denominator is 2. So you're gonna multiply all of them times 2. So 2 times half gives 1, and 2 times half gives 1, 1 times 2 gives 2. And then you're gonna confine them in a square bracket. So it should be written like 1, 1, 2. This indicates this crystallographic direction. It is, you're gonna just remove the spacing between them. So this is gonna give 1, 1, 2. This defines this crystallographic direction. It is 1, 1, 2. Then you're gonna do the same for any other vector. Okay? So it is the same procedure. So these are different vectors. You can try them. And I'm gonna give you some more examples how we can define these crystallographic directions in cubic crystal, like this case. Assume that, so something also that very important to understand. So the common between all of these vectors that they already projected starting from the 0 point. Like this vector, it is set up between the 0 point and another point, another atom. The 0 point and another point, and so on. So all of them are projected coming out of the 0 point. But the question is, should all the crystallographic directions, should we start them from the 0 point? No, it is not necessary. You can define the crystallographic direction between any 2 points, even if none of these 2 points is the 0 point or the origin point of this unit cell. Like in this example here, it is required to identify the indices of these different crystallographic directions in this cubic crystal. You should understand that it is cubic. It should be mentioned. So since it is cubic, it means that this edge is A, this is A, this is A. It means that all the edges are equal. Anyway, we do have so many directions. We do have direction A, which is shown by green. We do have direction C, this blue, and B, yellow, and the brown, which is D. So we need to identify the crystallographic directions of all of these different directions, or the indices of this crystallographic direction. For example, for direction A, it is set up between 2 points. This is gonna be the start point, and definitely this is gonna be the end point. All the time, the arrow is directed towards the end, start to the end. So this is the direction, as already given here for this vector A. None of these 2 points, the start to the end, is a 0 point. No problem. You're just gonna start from the start and move parallel to X, Y, and Z till you reach to the end point to specify this crystallographic direction. So what does it mean this? This means that is fine that if we define a crystallographic direction for any vector between any 2 points, even if none of these 2 points is an origin point or 0 point of this unit cell, that is fine to do so. Like vector A. So for direction A, what should be the crystallographic direction? So you're gonna start moving from the start point. So if you already starting here, how long you should move parallel to X and Y and Z till you reach to this end point? So for example, if you're already starting here, I'm gonna move parallel to this edge. What is this edge? It is Y edge. It is parallel to Y. It means that you're gonna move the entire B. So we remember that we should have X, Y, and Z. So I'm gonna move parallel to Y, the entire B distance, and I'm moving in the positive Y direction. I'm moving in the positive Y. So I'm gonna move this direction. Then I'm gonna move parallel to the X, but going to the negative X direction. As you can see, I'm moving negative. I'm not moving parallel to the or toward the positive direction of X, and instead of moving in the negative direction of X. So I moved parallel to Y, then I move to the negative X, the entire A edge. So it is negative 1A, the the 1%, the 100% of the complete A, but it is negative. Then I end up to this endpoint. It means that you shouldn't move anything parallel to the Z direction. You will not move anything parallel to Z. It means that it is 0 Z. So this gives us -1 and 1 and 0. So what should be the crystallographic direction? Is there any fractions? No, all of them are integers. So we are in a good shape, so that's fine. So it's going to be -1. Remember that the negative should be over on the top of the index, and 1, 0. So this is going to give us the crystallographic direction for direction A. Make sense? How about direction B? If we decided to do it for direction B, we're going to do the same. For direction B, this is the start point and this is the end point. Remember, as already given here, the end point is located in the middle of this face. It is half and half. Half of half, it means that it is located in the middle of that face. Like the FCC crystal structure, there is an atom that is located in the middle at the center of this face. And we're starting from this 0 point. So what we're going to do, your objective is just to define how long you're going to move parallel to X, parallel to Y, and parallel to Z. So if you're starting from here, how long you're going to move parallel to X? Are you going to move the entire X or half of it? No, you're going to move half of it because this is located in the middle, in the center of this surface. One of the simplest approaches, by the way, is to try to reach any one of the corners of this face. Just to not be confused, this is the simplest way. Try to reach from the 0 point, from the start point, this is the start point. Try to move to any one of the 4 corners of this face. So what you're gonna do, I'm just gonna move parallel to Y, this entire distance. I reach to this corner which belongs to this face. It means that you're gonna move the entire B edge in positive Y, so it is 1B along Y. Then what? How long you're gonna move parallel to Z? You're gonna move parallel to Z half of this edge, which is half C. Then till you reach to this point, then you're gonna move parallel to the positive X in this direction till you reach to the end point, half of X. Half of X, it means half of A. Make sense? So you're gonna end up with half, 1, and half. What is the largest denominator is 2. So you're gonna multiply all the indices times 2. So this gives 1, 2, and 1. So the crystallographic direction becomes 1, 2, 1 enclosed in square bracket. Make sense? Last 2 examples, let us consider this another set of directions which is different than this one. So let us consider, for example, direction B and C. So for direction B, we should find the X, Y, and Z distances, how much they are, or indices. So you should define the start point and the end point. So this is going to be the start point and end point. If you're starting here, how long you're going to move, or to reach to this point, I'm going to move this distance along this edge, then I'm going to drop down. Very simple, 2 steps, right? So how long you're going to move here? You're going to move 2 over 3 along the X direction, but you're gonna move towards the negative X because we start from here. So you're gonna move to the negative X, 2 over 3. Make sense? Because you're gonna move back this distance. This distance is 2 over 3 as given here. So you're gonna move to the negative X, 2 over 3. So negative 2 over 3 of A. How long you're gonna move parallel to, then you're gonna drop down. Moving down, this is parallel to Z. It means that how long you're gonna move parallel to Z, you're gonna move half of it because this is located in the half, in the middle of this edge. So you're gonna move half of the C, but you are moving in the negative Z. You are moving down, negative Z, in the negative, towards the negative Z direction, till you reach to the end point. This means that you will move nothing along the Y. There is no movement along the, or parallel to the Y axis. So this gives these indices. So we end up with negative 2 over 3, 0, and negative 1 over 2. Make sense? Then your objective is just to choose a number that when it is multiplied times these three indices, you should end up with all of them are integers. So the first thing actually, and it should be the smallest integer value. It should be the smallest integer value. So you have to choose the smallest denominator. I mentioned before it should be you choose the largest denominator. No, it should be the smallest, since we are seeking the smallest integer sets. So choose the smallest integer denominator first. So what is the smallest denominator here? We don't have 2. We don't have either 2 or 3. So the smallest of them is 2. So we're going to multiply all these indices times 2 first. But remember, this will not necessary to give all of them at once integers, as I'm going to show you. So if you multiply times 2, so if we multiply times 2, this is going to give us the negative 4 divided by 3, right? Multiply times 2. So we are multiplying times 2. So this is going to give us also 0, and here we're going to end up with negative 1. Now we still have a fraction. It means that we have to get rid of this 3. So we're going to multiply times 3. All the indices, yes, all of them. So this is going to give us negative 4. We get rid of this denominator and 0 and negative 3. Remember, you multiply times 3. So this is going to give us the vector as the negative 4 and 0, negative 3. So for direction C, what should be X, Y, and Z as usual? So we start from here. Remember, this is 1/3 that is given. It means that this vertical distance, this vertical height, it is 1/3 of this C. And so, but we start from here. Then we should move all the way till this end point. This end point is located at the center of this face. So as I said, the easiest approach is to try to reach to any point, corner or any point that belongs to this face. So what you're going to do, if you already start here, if we already start from this point, if you try to move parallel to y-axis, just move parallel to y-axis, we're going to reach up to this point, right? Then we're going to move parallel, we're going to move vertical a certain distance, then we're going to move parallel to the x direction. So we're going to move first, we're going to move parallel to y in this edge. How long? We're going to move the entire b edge. So it is 1b. And it is positive y because we're going to move toward the positive y direction. So we moved all the way till this point. Then we still need to move up a certain distance, right? This vertical distance, it should be the difference between this height, because this height it is half, right? But this height here it is 1/3. So the difference, this is what you should move up. We have to move up a certain distance till we reach here. Then we're gonna move inside to reach to the end point. We should have 3 movements, parallel to y, then z, then x. You got it? So I move parallel to y 1b. How long you gonna move parallel to z? You're gonna move the difference between half negative 1/3 of c. This is the distance that you're gonna move parallel to z. Then how long you're gonna move parallel to the, how much of distance you're gonna move parallel to x? You're gonna move half of the a. So you're gonna move half of the edge a. Make sense? If you did the calculation, just do the calculation of this value. This is gonna give us 1/6. This is gonna give us 1/6c, and we do have here 1b, and we do have here half a, and all are positive because you're gonna move parallel to positive y, positive z, positive. I'm sorry, negative x. It should be negative x, because you're gonna move in the negative direction for x. You have to double check of these signs. So this is gonna give us negative half, 1, and 1/6. Now we need to get rid of the denominators. What is the smallest denominator? There is 2. You can start from the smallest denominator. In some cases, like in the previous example, for example, we multiply times 2, then 3. It means that you're going to multiply times the multiplication of the denominators. But it is not necessary to be this way all the time. You have to take it step by step. Start from the smallest denominator. If there is one more fraction, multiply again to get rid of it. But the result, despite for this example, the result that we gonna end up, I can end up with one step. If I multiply these three indices times 6, which is 2 times 3, the multiplication of these two denominator, you're gonna end up with integer, but this is not necessary to be happening all the time. It is preferred to start with the smallest index, then if there is one fraction still, you're gonna get rid of it by the multiplication of this index. Make sense? Or the denominator. As I'm gonna do here, I'm gonna start with the smallest index or the smallest denominator, which is 2. So I'm gonna multiply first times 2. This is gonna give us -1. Then 2. Then 2 over 6, which is equal to 1/3. Make sense? Now I still have a fraction, which is 1/3. It means that I should multiply times 3. So if you multiply times 3, this is going to give us -3 and 2 and 1. I'm sorry, 6 here, because you multiply times 3. So 3 times -1 gives -3, 2 times 3 gives 6, and we're going to end up here with 1. So as you can see, we multiply times 6, not the 12, not the multiplication of the denominator. The multiplication of 2 times 6 gives 12. We didn't multiply times 12, but instead we multiply times 6, which is 2, then 3. So it is preferred to do it this way. Start with the smallest denominator, then if there is one more fraction, multiply by its denominator to get rid of this fraction. And this is what we have done. We multiply times 2. We end up with this one. We still have 1/3. We multiply by 3 to get rid of this 3. So this is going to give us the last combination of the indices as -3, 6, 1. This is going to give us the crystallographic direction for vector or direction C. Make sense? So this is simply how we can do the calculation for the crystallographic directions of cubic crystals. Alright, so now the equivalent crystallographic direction. So what is an equivalent crystallographic direction? We discussed these directions and we said that for any cubic crystal, for example, we're still focusing over the cubic crystal, we do have multiple directions, like this direction 0, 0, 1, -1, 0, 0, 0, 0, 1, 0, and so on. So all of these are different crystallographic directions. So are they equivalent or not? So what is an equivalent crystallographic direction? Equivalent crystallographic directions are the ones with different indices. So the index here, the indices are 0, 0, 1, but this one is 0, 1, 0. So these are two different indices. It means that this indicates that they are two different directions, but they are still equivalent based on one condition. What is this condition? That the spacing between the atoms along each direction is the same. Or in other words, if we decided to deal with it like in terms of mathematics and deal with this direction like a vector, it means that the magnitude, if the magnitude of this vector is the same, if these two vectors or two different directions is the same, it means that they are two equivalent crystallographic directions. So again, if you have any two directions, it means that they should have different indices, like 1, 0, -1, 0, 1, -1, 0, 0, these are two different directions. Are they equivalent or not? There is a test. There is a condition. What is this condition? That the spacing between the two atoms that represent these two directions should be the same. We said that any direction it is set up from a start to the end point. It means if the length of this direction is equal to the length of the second direction, they are equivalent. But if they do have different lengths, it means that they are not equivalent crystallographic direction. How we can calculate the lengths? You can do it as we used to do for mathematics, for the vector, to find the magnitude of a vector. For example, how long is the length? What is the length of this vector? 0, 0, 1. So it's going to be 0 squared plus 0 squared plus 1 squared, which is 1. You got it? So simply to find the length of any direction, crystallographic direction, multiply or sum the squares of the indices under the square root. This is going to give you like you are finding the magnitude of a vector. Like this one is going to be 1 squared plus 0 squared plus 0 squared gives 1. So the length of this vector it is 1, the length of this vector it is 1, the length of all of these vectors or all of these directions are 1s. So all of them, they are equivalent vectors, equivalent directions. So for example, directions 1, 0, 0, negative 1, 0, 0, negative 0, 1, 0, all of these directions are equivalent directions. These directions belong to one family written in this way, like this symbol, this special bracket 1, 0, 0, or 0, 1, 0, or 0, 0, 1. It means that this is a family and we're gonna discuss what is a family. We can write this symbol as this special bracket by 0, 1, 0, or we can write also 0, 0, 1, this special bracket. So now we discuss two things, two types of bracket. The square bracket, if you confine any three indices within a square bracket, this indicates a crystallographic direction. If you confine any three indices between this special bracket, this indicates a family of equivalent crystallographic directions. So what is a family? It is a group. The family, it is a group of multiple crystallographic direction, but the condition is that all of these directions are equivalent crystallographic direction. So we can define a family of directions as a group of equivalent crystallographic directions. Make sense? The common between all of these directions is that their lengths or the spacing between the atoms is the same. This is the condition. As I mentioned, all of these crystallographic directions, they are equivalent. So we can combine all of them in one family and we name this family as 1, 0, 0 or 0, 1, 0 or 0, 0, 1. Why this value? Because the magnitude, if I ask you to calculate the length of this magnitude, how much it is 1 square plus 0 square plus 0 square gives 1, 0 square plus 0 square, 1 square plus 0 square under the square root gives 1, 0 square plus 0 square plus 1 square gives also 1. So any way of representing the value, the family, we're still talking about the same family. So we can write this family as 1, 0, 0 or 0, 1, 0 or 0, 0, 1. Any option is fine since the length of this vector, it is still the same. Okay, so this is what does it mean an equivalent crystallographic direction, and what does it mean a family? A family is a group of equivalent crystallographic directions. There is a very important notice here that you should consider for all cubic crystal. This is commonly for any cubic crystal, whatever it is, FCC, BCC crystal structure, anything. Any crystal structure that belongs to the cubic system, this condition or this thing is applied to it. For cubic, this is only for cubic crystal. Directions having the same indices with no regard to their order or sign, they are equivalent directions. For example, negative 2, 1, 3, negative 2, 1, negative 3, this is a direction. This is crystallographic direction, and we have another crystallographic direction which is 1, 2, 3. They are having the common between these two directions is one thing, that they are having the same indices, that there is one index is 1, one index is 2, one index is 3. But the arrangement, the order of the indices is different. It's different. Here we would have 2, 1, 3, here we would have 1, 2, 3. Also, there is a difference in the sign. Here we would have negative 2, here we would have 2, positive 2. We would have negative 3, here we would have positive 3. So the common thing between these two vectors is one thing, that they do have the same indices, but the arrangement of the indices or the sign of the indices are different. But these two, this is as long as they belong to cubic crystal, only for cubic crystal. So for only cubic crystal, any two vectors with the same indices, with no regard to the sign, with no regard to the order of the indices, they are two equivalent directions. So these two directions are equivalent, despite that they do have different signs, different order of the indices, but they are equivalent. What is the condition? The condition is that they belong to a cubic crystal and they do have the same indices. So what does it mean this? For example, if you do have a vector 4, 1, 3 and another, or negative 1, 3, and we do have another vector which is 1, 3, 4, and both belong to the cubic crystal, to a cubic crystal. Are they equivalent directions or not? Yes, they do equivalent. Why they are equivalent? They do have the same indices, but they do have different signs, no problem. They do have different order, no problem. Still equivalent to directions, two equivalent directions. Make sense? So these strengths of the crystallographic direction that we mentioned here, you can apply the same procedure and represent the crystallographic direction by 3 indices for any crystal system of the 7. Of any of the crystal systems, the 7 crystal system, cubic, hexagonal, tetragonal, trigonal, anything. But there is a problem with this hexagonal crystal system. If we decided to represent the crystallographic direction using 3 indices, we're gonna face a problem. There is a trouble here. What is wrong with this hexagonal? Okay, so in the hexagonal, a problem arises of crystal having hexagonal symmetry, or the hexagonal crystal system, that some crystallographic equivalent directions which defined by 3 indices will not be set in one, will have the same set of indices. Like as we mentioned, for example, to have equivalent indices, they should have, or equivalent, two equivalent directions, they should have the same indices with no regard to the sign, with no regard to the order of these indices. If we try to do the same thing for hexagonal crystal structure, this will not be acceptable. This will not be applied. It means that the same indices, or this will end up with different indices or different lengths even. If we decided to use 3 index annotation or representation for the crystallographic direction as we did for the other crystals. So there is a problem. How we can fix this one? It is better to use 4 axes or something that is known as nor-brevis coordinate system instead of the conventional coordinate system for this hexagonal crystals only. So for hexagonal crystals, to get rid of this problem that you may have some of the crystallographic directions which should be equivalent, when we define their direction by 3 indices, this will not give the same set of indices, and we're gonna end up with trouble here. So it means that you are gonna able to judge whatever they are equivalent or not if you decided to represent these directions of the hexagonal crystal using 3 indices. To fix this problem, we have to use 4 indices instead of 3 indices. So what are these 4 indices? When we define the crystallographic direction using 3 indices, as we did for cubic crystal, for example, these indices indicated the fractions, how long you're gonna move parallel to X, Y, and Z. So in general, we do have 3 directions. We do have 3 coordinate system. We do have X, Y, and Z. So it makes sense that you represent the direction using 3 indices only. How about the 4th index? How it belongs? This means that you're gonna use a different coordinate system, which is different than the conventional coordinate system that all of us know. That is different than X, Y, and Z. So for example, if you decided to represent, this is a hexagonal crystal structure, and you decided to work with 3 indices, so you should set up X, Y, and Z. Like A1 is gonna be like X axis, and this A2 is gonna be Y axis, and this is Z axis. If we decided to work in conventional as we did before. So you're gonna, for example, to define this vector, which is shown by green, so this is gonna be the start point, then you're gonna have the end point. Your objective is just to move parallel to X, then you're gonna move parallel to Y, then you're gonna jump up vertical parallel to Z to end up, to reach to the end point. This is gonna give you 3 indices, which will be U dash, V dash, W dash, and then you're gonna include them in a square bracket. So let us refer to U dash, V dash, W dash, these are the indices. If you decided to work conventional, if you decided to work using 3 index, if you decided to work with X, Y, and Z axis as conventional, where U dash, this is the displacement parallel to X, V dash, this is the displacement parallel to Y, and W dash, this is the displacement parallel to Z. Very simple as we did before. But there is a problem with this system. We have to convert it from 3 index to 4 index. From 3 indices to 4 indices using Miller-Brevis coordinate system. This is a different coordinate system which is different, known as 4 axes coordinate system, 4 axis coordinate system, which is different than the conventional one. How this Brevis or Miller coordinate system is set up, we're gonna set up A1, A2, A3, and Z. There is no X, Y anymore. You're gonna have A1, A2, A3, and Z. So you're gonna to define a vector, you're gonna measure how long you're gonna move parallel to A1, not X. There is no X and Y anymore. How long you're gonna move parallel to A1, how long you're gonna move parallel to A2, how long you're gonna move parallel to A3, so these are 3 entries, and how long you're gonna move parallel to Z. So 4 steps. And instead of moving 3 steps, you're gonna move 4 steps to move from the start to the end of a vector. So this is gonna give you 4 indices, which are U, V, T, W. U is movement parallel to A1. V is movement parallel to A2. T is movement parallel to A3, but W is movement parallel to Z. Make sense? So these are 4-axis coordinate system known as Miller-Brevets coordinate system. How we can convert, if for some reason, if you identified U dash, V dash, W dash, how you can define the 4 indices. If you already given the vector for a hexagonal crystal with the 3 index notation, how you can convert it into 4 index notation. You're gonna use this relation. So the relation between U and U dash, V dash, W dash, this is how we can calculate U for given U dash, V dash, W dash. So U equals 1 over 3 times 2 U prime or dash negative V prime. This V equals 1 over 3rd, 2 V prime negative U prime, T equals negative U plus V, but W equals W dash or W prime. Make sense? So this is simply how we can convert from the 3 index notation to the 4 index or the Miller-Brevets coordinate system for the hexagonal coordinate, for the hexagonal crystal. So if we are interested in writing this direction, which is given as 0, 1, 0 in the 3 index notation or 3-axis system in terms of the Miller-Brevets 4 index system, how we can convert from 3 index system to 4 index system. So your objective first is just to define how much is U dash equals 0 according to this index. V dash is gonna be, or V prime is gonna be 1, and W prime is gonna be 0. Make sense? Then you're gonna use these things and substitute into this equation to end up with U, V, T, W, which are the 4 index notation. Very simple. Direct calculation, direct substitution. So this is gonna give us U equals 1/3 times the double of U prime, which is 0. So it's gonna be 2 times 0, definitely will be 0. Negative V prime, which is 1. So this is gonna give us 0 will be, you're gonna end up with negative 1/3. You have to acknowledge the sign. How about V? V, it will be 1/3 times 2 V prime, which is just 1, negative U prime, which is already 0. So this is gonna give us 2/3. How about T? T is gonna be 1, is gonna be negative U plus V. Remember, that's it. Just observe this thing. This is U, not U prime. This is V, not V prime. U that you just calculated by negative 1/3. We calculated U by negative 1/3 plus V, not V prime. V, it is calculated by 2 over 3. It is 2 over 3. So this is gonna give us 1/3 times negative. This is gonna give us at the end negative 1/3. Remember that this is U, not U prime, V, not V prime. And W, it will be W prime. So this indicates that W will be W prime, which is 0. So we're gonna end up with 1 index 1/3, negative 1/3, 2 over 3, and negative 1 over 3, and 0. So we have fractions. We agreed that the vector, it should be represented by integer values. So we have to get rid of the fractions. We have to get rid of this denominator. So you're gonna multiply all the indices by the same denominator, by the same number, integer value. So all the denominator, the common between them is 3. So if you multiply to get rid of them, multiply all the indices by times 3. So this is gonna give us, if you multiply times 3, this will be converted into negative 1. And this will be converted into 2. If you multiply times 3, and this will be converted into negative 1. And this definitely will be 0 as it is. So this is gonna give us the 4 index vector will be represented as negative 1, 2, negative 1, 0. The order, you have to acknowledge the order. The order is U first, then V, then T, then W. Make sense? Which gives you the the vector, the same vector, but in the Miller-Brevets 4-index system, which is a different thing. So they are equivalent thing. This, you still representing the same vector, but instead of using 3 indices, you're gonna use 4 indices. What is the benefit of using 4 indices? Now we can correctly define all equivalent crystallographic direction that belong to hexagonal crystals. Make sense? This is just for hexagonal crystal, not for any other crystal. The other crystal, you're going to use the 3 indices system as we explained before. Now let us consider some examples here, how we can define these vectors. So now the vector or the indices were given. And then we just converted into the 4-index system using these equations or these relations. But how about how we can find, even for a hexagonal crystal, how we can identify these 3, then we are going to convert to the 4-index notation. Like in this example, it is required to determine the indices for the direction that is shown for the hexagonal unit cell in sketch A in this figure. So this is the direction that is given. You are required to represent this direction in the 4-index system, in the Miller-Brevets coordinate system. Make sense? So you have to find u dash, v dash, w dash, or u prime, v prime, w prime first, which are these 3 values. Then you're going to substitute into these relations. You're going to end up with the 4-index, very, very simple. So how we can find u prime, v prime, w prime? This is the critical part. This is the challenging part. To do it, actually, I'm just going to give you a very simple approach. Your objective is just to draw this hexagonal base. And over this hexagonal base, you're going to define, remember that A1, A2, A3, Z, these are the 4 index or the 4 coordinate or axis system. But in the A1, A2, Z, this is how you're going to work. You're going to work over this one, over this coordinate system. So your objective is just to draw this hexagonal base and assume that the Z is already projected out of the drawing paper. Like, for example, I'm just going to draw the hexagonal base in this way. Make sense? And then over this hexagonal base, your objective is just to define A1 and A2 axes. A1, A2 like X and Y. You're going to work like 3 index. When you do the calculation, because I need to calculate U prime, V prime, W prime, so you should consider 3 index system. 3 axis coordinate system, not the 4 axis. Make sense? So this is the 0 point. This is the origin, which is going to be this point in the middle. Then you, over this hexagonal, there are some vertices or there are some corners. So you're just going to connect this corner to this 0 point and you're going to define A1. A1, this works like x-axis. Remember that U prime, this is how long you're going to move parallel to A1. And then you're going to skip one vertex and then you're going to connect to the next one to define A2. And remember, some of the specification that you should understand about the geometry of the hexagonal shape, that this angle, it is 120 degrees. This is what you should understand. It is not 90 degrees. Make sense? So your objective is just to define A1 and A2 direction like X and Y. So the distance that you're going to move parallel to A1, this is going to give you U prime. The distance that you're going to move parallel to A2, this is going to give you V prime. The distance that you're going to move vertical parallel to Z, this is going to give you the W prime. So what is the vector? The vector is given here. This is the vector as represented here by green. So this is the start point. If I ask you to move from the start to the end point, how long you're going to move parallel to A1, how long you're going to move parallel to A2, then how long you're going to move parallel to Z till you reach to the end point. The Z, it is not a big deal. The Z is easy thing. U prime is very simple, but the challenge is how long you're going to move parallel to A1, how long you're going to move parallel to A2. So in this projection, in this representation, your objective is just to find the projection of this vector over this plane. So this vector, as you can see, this is the end point. Can you locate this end point over this base? If you're going to look to this hexagonal crystal from the top, this end point will be directly on the top of this point on the base, which is this one. Do you agree? Like you should have the vector. The vector is, it moves from this start point, which is going to be this 0 point. So this is going to be the start, right? And what is the end point? The end point, it should be on the top here. But the projection of this point on the top view, vertical, if you just gonna look at it from the top, you're gonna find that this point is directly on above this point that located in the base, which is this one. This means that this should be the end point somewhere here. So if you just connected these 2 points together, they should give you the projection of this vector, but on the top view, on the base, over the base. Then your objective, because as I said, the W prime, it is very simple. W prime, we can get it from the shape. There is no big deal with the W prime. But the challenge is how you define U prime and V prime. So simply, your objective, if you start from here, how long you should move parallel to A1 and parallel to A2 till you reach to the end point. So simply I can move parallel to A1. I can move parallel to A1 over this edge, right? Then I'm gonna move parallel to A2 over this edge till I reach to the end point, because this edge is already A1 and this edge is parallel to A2. So I'm gonna move in the positive A1. So if I just write here A1, I'm going to move parallel to A1 with this distance. This distance, it is equal to the A. Remember, some of the specifications of the hexagonal geometry is that this side it is A, this side it is A, this side is A. All of these sides, all of these edges are equal to A. From the hexagonal HCB crystal structure that we explained before. Also, this distance is A, this distance is A. So this is A, this is A, this distance is A, this distance is A. All of these lines are equal to A. These are the specification of the hexagonal crystal structure. So what does it mean? This means that you're gonna move parallel to A1. How long? You're gonna move parallel to A1, the entire A. 1A. Then how long you're gonna move parallel to A2? You're gonna move parallel. So I'm gonna move parallel to A1 first. Then I'm gonna move in this direction parallel to A2. How long you're gonna move parallel to A2? I'm gonna move 1A as well, the entire A, the entire edge. And both are positive. Why positive? Because you're gonna move positive A1, positive A2 till you reach to the end point. So I specified A1 and A2, how long these directions. This means that U prime is gonna be 1 and V prime is gonna be 1. This is how you can define U prime and V prime. You have to draw, represent the vector over the base. This is the easiest approach. Then just investigate how long you're gonna move parallel to A1, how long you're gonna move parallel to A2. Remember that all the edges, all the distances are A, are equivalent, are the same. Equal to A, which is the side edge of the base of the hexagonal crystal structure. And we agreed that the C is different, equals to 1.663A from the last video. So we still need to define how much is W prime. W prime, this is the height. So since we reach, so we move from this point, parallel to A1, A2, we reached up to this point. How long you're gonna move vertical to get the exact end point of the vector? You're gonna move the entire C, you're gonna move the entire height. So this means that W prime will be 1C or 1. Then you define U prime, V prime, W prime. Your objective is just to substitute into this relation to calculate how much is U, V, and T and W. Make sense? So this is how it works. You have to set up the base first, investigate the challenges with U prime, V prime. Investigate how much is U prime, V prime. W prime, it is not a big deal. Then you're just gonna substitute. U equals 1/3, 2 times U prime negative V prime. Do the calculation. This is gonna give us 1/3. And V equals 1/3 to V prime negative U prime. This is gonna give us another 1/3. T equals negative U not U prime plus V not V prime equals -2/3, and W will equal to W prime equals 1. These relations are fixed relations that you're gonna substitute. Once you find U prime, V prime, W prime, plug them here, you're gonna end up with these values. Then you have to get rid of the denominator. The denominator, all of these denominators are 3. You're going to multiply by 3. You're going to end up with 1, 1, negative 2, 3. These are the 4 index representation of the crystallographic direction as represented for this given hexagonal unit cell. Make sense? Another example here, how we can define this crystallographic direction for this crystal, hexagonal crystal. Let us start with the simplest one, which is this one. This is very simple. If you start from here, how long you should move parallel to A1 and A2? Forget about A3. You need to define first U dash. So let us give number, like this is vector A and this is vector B and this is vector C. So, or direction A, direction B. So let us start with direction A. What should be U prime, V prime, W prime? How long U prime, how long you gonna move parallel to A1? Are you gonna move anything parallel to A1? No. Are you gonna move anything parallel to A2? No. The only movement, there is just one step. One step that you start from here and this is the end point on the top. It means that you're gonna move parallel to Z with the entire height, with the entire C. So it means that U prime is 0, V prime is 0, but W prime is 1. You will not move anything parallel to A1 or A2. The only movement is parallel to Z. So then you're gonna plug these relations into the U. These 3 values into the U, that is equal. According to this relation, it is 1/3 to U prime negative V prime. Then equals U prime, V prime are 0. This is gonna give us 0. Then V equals 1/3 over 2 V prime negative U prime. Both are 0. This gives 0. And T equals negative U plus V, which are 0 plus 0 equals 0. And W will be W prime, which is gonna be 1. This is gonna give you the direction or the crystallographic direction for direction A. It is the U is 0, the V is 0, the T is 0, but we do have 1. So this is gonna be 0, 0, 1. Make sense? How about direction C? Let us skip direction B because it is a little bit tricky, but let us move to direction C. For direction C, we have to draw the base. For direction A, it is only one movement parallel to Z, so there is no need for the base. There is no movement for A1 direction or A2 direction, so that's why we didn't draw the base. But for C, you have to draw the base so you can investigate the correct direction, how you're gonna move to find U prime and V prime. So for direction C, which should be this direction C, your objective, as I mentioned, just to draw the base, the hexagonal base. Your drawing, it is not necessary to beneath any drawing, just represent the A1 and A2. Remember that you just gonna pick this vertex, this corner, skip one and choose the second one to define A1 and A2. Where should be the end point? So this is the start point of vector C, which should be the 0 point. The end point is gonna be here, right? So define this end point over the base, which it should be this one. It means that this direction, it should be direction C. So if you're starting from here, how long you're gonna move parallel to A1 and A2 to reach to the end point? So if you move parallel to A1 in this direction, then you're gonna move parallel to A2 over this edge, you're gonna reach to the end point. Very simple. This edge is parallel to A2 and this edge is already over A1. So this edge is parallel to A1, this edge is parallel to A2. So how you gonna move? I'm just gonna move parallel to A1 and parallel to A2 till I reach the end point. How long you gonna move parallel to A1? I'm gonna move the entire A, and I'm gonna move parallel to A2 as the entire A. So it means that U prime and V prime, W prime. Forget about W prime for now. U prime will be 1A and V prime will be also 1A. V prime, this is the 1A4 that is parallel to A2. How about W2? If you reach to this point over the base, if there is any movement vertical to draw the line C, no. The Z direction for this vector here is 0, so the W prime 0. You won't gonna move. We started from here. We move parallel to A1, then A2, I reach to this point, and that's it. So it is 1A, 1A, and 0. It means that U prime will be 1, V prime will be 1, W prime will be 0. Then what? You have to calculate U equals 1/3 times 2U prime negative V prime equals. U prime it is 1, so 2 times 1 this is 1/3. It is 2 negative 1 gives 1/3, so it will be 1/3, and V equals 1/3 over 2V prime negative U prime, as I remember the relations, right? Yes, exactly. And this is gonna give us the 2V prime will be 2 negative 1 gives 1 times 1/3 equals 1/3, and T equals negative U plus V, which is gonna be the U plus V gives 2/3, so this is gonna give us negative 2/3, and W will be W prime, which is gonna be 0. Then you have to multiply times 3 to get rid of the denominator, so this is gonna give us the vector as, or the direction as 1 and 1 and negative 2, because this will be negative 2 and 0. So this is gonna give us the crystallographic direction for this vector C. How about vector B? Vector B, this vector is a little bit tricky. Why? Because as you can see, it is somehow in the middle of this edge. So if we decided this is for direction B, if we draw the hexagonal base, and this is going to be the 0 point, this is going to be the A1 direction, like the x-axis, and this is going to be the A2 direction that define V prime. What is vector B? Vector B should be drawn going down, as shown here. It is, if this is the start point, it means that in the middle of this line, you're just going to connect this point to this point. This is going to give you the direction B. How we can define the U prime and V prime for this direction B? There are different ways. I'm just gonna try to give you the simplest one, but I'm gonna give you the complicated method first. So as usual, as we used to do, your objective is just to specify how long you're gonna move to parallel to A1 and A2 till you reach to the end point of this vector. Okay, so if we start from here, simply I'm just gonna move A1, right, in this direction. You're just gonna move parallel to A1 in this direction, in this way, the entire A. Then your objective is just to move parallel to A2. But if I try to move parallel to A2, I should move this way. So you aren't gonna reach, you skip the end point. So the other option is, the complicated way, is just to try to do like the projection, find the projection of this line. Do you see this distance? This is the distance that you should move. So you're gonna calculate this distance, which it should be half A, because this entire edge, it is A. So this distance, it is half of A. This half of A will be projected over this A1 and A2, and do some trigonometric calculation. You're gonna spend like half an hour, and probably you're gonna end up with some wrong results at the end. But the easiest way is, and this is another thing that you should consider, here we are seeking a direction. We are seeking the direction, not the position of a point. So what does it mean this? It means that it is not necessary that you consider that the end point is this end point. I can consider any other point that belongs to this direction as an end point. I'm seeking the direction, I'm finding the direction, not the location of a point. So what does it mean this? If you try to consider that the end point, if you consider the end point is over this edge, it will be kind of complicated to do so. But the easiest way is just to assume that this vector is continuous, is just keep going down. And if you try to, this edge, the extension of this edge, and the extension of this edge, they should meet together at a point which should give you the end, another point that belongs to this vector. Because this edge is A, this is A, this is A, and this should be in the middle of this edge. It means that if you extended this vector up to here, it will be at the intersection of this edge, the extension of this edge with the extension of this edge. Both they're gonna meet together here. So now I'm gonna deal with that. This is the start point, and I'm gonna consider the end point is down here, not this one in the middle. If you consider this one in the middle, it will be complicated to figure out the trigonometric things. Make it easy. I'm seeking direction, not seeking end point or coordinate of a point. You got my point? So I need to find the direction. I don't care about which point exactly the end point. Any 2 points belong to this direction, I'm gonna consider one at the start, the second one at the end. Any 2 points along this line. So that is fine to extend the vector down to another crystal. Now I moved outside the boundary of the crystal, no problem, that is fine. We can do so. And then your objective is just to calculate these directions. So if I ask you to calculate how long you're gonna move barrel to A1, I'm just gonna move barrel to A1 this distance, which it should be the entire A. Then you're gonna move barrel to A2. I'm gonna move barrel to A2 with this entire distance, which is also A. But remember that A2 you're gonna move in the negative A2 direction, but positive A1 direction. This means that U prime will be positive 1 because you're gonna move the entire A in A1 direction, and V prime will be negative 1. Why V prime is negative? Because you're gonna move in negative A2 direction. How about W prime? W prime, you're gonna figure it out from the entire crystal, not from this plane. The W prime will be 0. Why 0? Because this vector, it is coincident over the base. It won't gonna jump up. There is no vertical displacement till the end point of this vector. It means that it is not standing, it is over the base. It means that W prime will be 0. Then what you're gonna do, you're just gonna do the calculation using U equals 1/3 times 2U prime negative V prime. This is gonna give you 2 times 1 gives 2, negative. Negative gives positive. Remember the calculations. It is 2 times 1 gives 2, negative times negative V prime will be positive 1. So this gives 3, will be cancelled with the denominator, you're gonna end up with 1. V equals 1/3 times 2V prime negative U prime equals 1/3 times 2V prime. V prime equals negative 2. So this is going to give it, because V prime equals negative 1. So negative 1 times 2 gives negative 2. Negative 1 gives negative 3. Will be cancelled. The 3 will be cancelled with the denominator, gives negative 1. And the T will equal to the negative U plus V. U equals 1, V equals negative 1, so this is going to give us 0. They're going to cancel each other. W equals W prime, which is already 0. So we're going to end up with 1, negative 1, 0, 0, all are integers. So there is no need to multiplication of anything because there are no fractions. So we're going to end up with the vector as 1, negative 1, 0, 0. Is a double 0, I'm sorry. Okay, so this is gonna be the 4 index crystallographic direction for the hexagonal crystal. So these are the 3 directions, and these are the direction that, as we specified, for this one it was 0, 0, 1. For this one was 1, 1, negative 2, 0, and 1, negative 1, 0, 0, as we defined them here. Make sense? So this is simply how we can define the crystallographic direction. So that's it for this video. This video we discussed how we can define the crystallographic points, the coordinates of a point, how we can define the crystallographic directions for cubic crystal or all the crystal systems, and then we discuss how we can describe or define the crystallographic direction using the 4-axis system or notation, especially just for the hexagonal crystals. Make sense? The next meeting we are going to discuss the crystallographic planes, and we're gonna know how we can define these planes for cubic crystals and hexagonal crystals as well. So that's it for today, and thank you, and see you in the next video.